we want to build the standard one? Well, for the time being, the electroweak part. Although we would do the strong part in exactly the same manner, using the same gauge principle. And of course, here the main ingredient was the Jungian theory developed by Shaw and Young and Mills in 1954. Which was the sort of mathematical generalization. At that time it was not clear, there were no new interactions, or you didn't think of them in these terms, okay? It was more of a group theory exercise, turned out. Profound and extremely important was to generalize the U1 gauge symmetry to any group, okay? Let's stick to the unitary groups for the moment. So if I take, how does the QED, the U1 example, work with the gauge principle? You say I start with Dirac equation. And I see immediately that there is a symmetry e to the I alpha phi, where where alpha is a constant, okay? This is the U1 global symmetry, which gives me the conservation of current. And let's do as we normally do. Let's keep Q here as a generator of that symmetry. Whatever that means at this point, it's not clear what it means, it's just a number, okay? Then you say, and of course from here you get a conserved current. Then you say I want to generalize it, I want to take alpha equal alpha of x. So I make it gauge. And what I want, I can't have this invariant anymore. I have to change the derivative into covariant one. So that d mu phi transforms. And let's call this transformation u, e to the I alpha x cubed. Now I have a unitary space-time dependent transformation, right? U dagger u is 1. The reason I want to write it this way, I can immediately generalize to any unitary transformation, right? Now let's write it in a generic language. This should also transform as u d mu psi. Then of course everything will be okay. Right? The Lagrangian will be invariant. If the covariant derivative transforms the way psi does, then this will be manifested derivative. U dagger here and u will give us. And I will introduce then u requires to introduce another function. And I've written it the most general way. I put a coupling constant, I put a charge here, and therefore this will just tell me how mu transforms. Okay. If I didn't put here E, then E I could write here, but then I'm changing normalization of the field, and it's not conventional. So this is the most general one, and then I say, this will go into I psi prime, which is psi bar, U dagger, gamma mu, d mu minus E A Q A mu prime, U psi. If I perform this transformation, at the same time, what is this U? Nobody. It's funny how silly things you can write when you're running ahead of yourself. Right? This is what will happen, okay? A will become A prime, psi will become psi prime, which I defined here. And this is Maybe I could have done this a little more elegantly. I left my notes at home, so there is nothing to look at, so we have to do this together. Starting to come here. Well, maybe it's enough that I look at the covariant derivative. Anyway, this is I. This must be equal to I psi bar gamma mu d mu minus I A Q A mu psi. Right? The new Lagrangian must be equal to the old Lagrangian. And from here, all I have to write down what is A mu prime. And maybe I just write down the result. Right? You've seen this many times. It turns out that Q A mu prime, I'm writing it in a silly manner, okay, which is not at this point useful at all, okay, but it will be good when I want to generalize it. It's going to look complicated. You will see that this becomes U, Q A mu, U dagger, minus I over G, d mu U, U dagger. That's because d mu acts on U here. It's kind of trivial. And I think I got the signs correctly. Please check me. You can even do it as I'm going on if you wish. I could have made a mistake here. That is plus sign. It wouldn't be such a big deal because I can always choose alpha to become minus alpha. It's not a fundamental thing. But the way I wrote it, maybe I should be consistent with myself. So this is the way the transformation would look like. And we can immediately recuperate. Everything commutes here. Okay, it's just a silly way of writing, maybe unnecessarily complicated at this point. We can find immediately the usual form of the gauge transformation. This commutes, so I get Q A mu minus I over G, and d mu U is I, sorry, d mu alpha, Q, and U dagger is 1. Sorry?
Do you have the Q in the last term in the first expression? With d
here, Q.
No, the upper one, the minus I G over G. The last term in the
here.
Yes, this one.
Here.
No, Q.
No. When d mu acts here, there is no Q. Q is only associated a mu the way I wrote. Q will not stay by itself. Q is hidden here. I put it in U.
Oh yes, yes.
Yeah, I don't guarantee for everything I write on the blackboard. You see how many mistakes I do. But this is correct. So it happened. I was lucky. Minus I times I is 1, so I will get that a mu prime is a mu plus 1 over G d mu alpha of x. Sometimes you may see a minus sign, even if I write sometimes minus 1. Sometimes I define U with a minus sign here. It's not a big deal. Why is this so useful, right? This equation here. Well, I can generalize. If I don't tell you what U is, now I got the most general equation in the world. All I have to remember that if I want now to go to a, say, some SUN group, there'll be more charges, more generators, but the principle will be the same, right? So let's do SUN now from U1. The only difference is that U is e to the I. I often write theta dA. Every unitary matrix can be written as E times Hermitian. And the Hermitian you expand in the basis of Hermitian. So I am asking that U dagger is U dagger U is 1. And the determinant U is 1. And this in particular means that trace TA is 0. This means that TA is TA dagger. So this is my usual basis, right, in the SUN group. We said in SU5 there will be 24 of them. The rest follows. So this equation gets immediately generalized. I will have TA, A mu A prime, equal TA, A mu A, minus, no, which, not this equation. I don't want this equation. I want this equation. The general one. U, sorry. U dagger minus I over G d mu U dagger. Now, of course, they do not commute. So look at the two pieces, okay? I know that you know Young-Mills, but I said, let me just make sure they have grasped all the essential points, okay? One is, for example, that here, because of non-commutation relations, right, TA, TB, do not commute. I have some structure constants that tell me how they behave under commutations. So there are two pieces here. The second piece is just a gauge transformation, right? The generalization of what happened to the Maxwell. But first piece tells me that the gauge bosons are sort of a funny thing. They are joint representation, that we say, of the group, okay? They transform. Even if you will now take the global transformation, they wouldn't be invariant anymore. They carry charges, if you wish. They're not neutral. Well, that's not so surprising if you go back and think what we said Wednesday, Friday. W boson carries charge, okay? That's what I found out when I was building SU2, carry the electromagnetic charge. But now, really, strictly speaking, I should be speaking of different charges. There may be many charges in a big SU2 group. And charge, sometimes people call this charge, which is sort of a little careless. It's a generator's charges we should associate with the Cartan subalgebra, with the rank of the group. So, for example, in SU4, there will be 4 charges. In SU5, sorry, the rank of SUN is n minus 1. You know that SU5, which I will be bringing up, will have 4 charges. We'll come back and think about SU5 for using reasons, okay? So what it means, look, from here, I can find immediately how A mu I prime is a function of A mu A. This would be, so let's do a small transformation, and let me just look at the at this piece. So this will go as 1 minus I TB theta B. Let me call TC A mu C. Here, that doesn't matter where I put the index, right? This is an internal index. It could be up, lower, okay? There is nothing funny in the Lorentz case. And I'll find immediately that this is equal to TA, A mu A. Don't be puzzled if I change the dummy index. I do it at will. In the second piece, I'm going to keep it there because I don't want to have the same A that is there in order to reproduce the complete result. And I will have minus I, theta B, TB, TC, A mu C. Correct? So this is TA. I'll take out. I will get A mu A. Minus I times plus I will give me plus 1. Right? And this is FBCA. I will introduce A now. That's FABC. That's the same thing. FABC. And here A mu C. No, theta B. A mu C. This is what we normally call a joint representation. Okay, when we have an SUN group, there are 2 representations which are extremely important to us. The fundamental, we build everything out of fundamental. Okay, that's a spin half. Every spin can be built out of spin half. But it's particularly interesting is the adjoint representation. For example, in the case of SU2, if I put F equal epsilon, so a small digression here, if I have SU2, then F is epsilon, and this adjoint is what? This transforms as a vector. That's a triplet of SO3. This is why we say that SU2 and SO3 are the same group. They are not, strictly speaking. They're the same algebras, okay? But you and I are going to worry about algebras only. Unless you decide that you're interested in magnetic monopoles and stuff like that, when the topology of the group matters, okay? This is a side comment. And at some point, any of you interested in this stuff, I could let you read something more. But when we speak of perturbation theory, or weak interactions, and we will be dealing with weak interaction in this class, all we need is the algebra, okay? We don't have to worry what happens at large distances. We don't have to worry about the topology of the group. So here, adjoint, so this is called an adjoint representation. And notice the advantage of using this language. If you use the language here, you would have to remember the structure constants, or, well, in SU2 you remember that. So you can work with a vector. But from now on, I'll try, even when I speak of SU2, not to use the vector, but to use the adjoint. Now why? Because then I can go to any group in the world. And I will show you on the way, if you don't know, that any group SUN can be built out of SU2. All you have to know is Pauli matrices, and then just sort of rearrange them, and the rest will follow. And it tells me that if the fundamental representation, so here in SU2, so the adjoint is vector. So in general, in SU2 it's easy to know the adjoint because epsilon is easy to remember. But in general, you don't want to remember F's. Even SU3, I'm sure you don't know them. I don't know. And I've been working with SU3 a lot. But I always remember Pauli matrices or Gell-Mann matrices. They're made out of Pauli matrices. So all I have to remember this underlying fundamental representation. Then the adjoint is made, look, it's just made out of fundamentals here. U is the fundamental. So this is very convenient. So here, what I mean when I say that TA would be a Pauli matrix properly normalized. And since I will normalize my non-abelian, as we call them, abelian U1, non-abelian show Yang-Mills, that we call Yang-Mills, I normalize this one in the same way, then of course the coupling constant has to be one and the same, otherwise you would have to normalize fields differently, you would lose the symmetry. This is why there was a question I think Mahmoud asked me. Of course there must be one and the same coupling constants if I normalize my gauge field one and the same manner, in order to keep the symmetry. So G is external to this. So I should only have written it, okay, in the SUN. I'm sorry, it should have been here, of course. The d mu is d mu minus IG dA, A mu A. We can build the tensors, the fields out of that, right? The Yang-Mills fields, the analog of Maxwell, electric and magnetic fields. They are a little subtle, but let's not do them today. It's not just the antisymmetric piece, right? There is an extra piece, which has to be there. Why? Okay, maybe just a question here. If I want to now generalize F mu nu, and it's going to be F mu nu A, as many of the A goes to 1, 2, how many there are in SUN? N squared minus 3 in SU2, 8 in SU3. F mu A is as many, of course, as there are potentials, A mu, as we call. Sometimes I call this field, sometimes potentials. Okay, I'm not very careful. This is only what we reserve for the field. Okay, when it's necessary, I'll be careful. When it's not, I won't. D mu A mu A minus D nu A mu A. How do you know that this will not be everything? It won't transform correctly. In other words, what you want from F mu A, you would like F mu A, this is the definition of F mu A. F mu A, TA, must transform as U F mu A EA U day. The Young-Mills field transforms as the adjoint representation. Of course, they cannot have the extra gauge piece. We need an invariant also will to build a Lagrangian. We start with the covariant thing. So how do you know that there will be an extra piece here? And do you remember what it is? Nicolas said, sorry? There is a commutator, I already put A, so you already reduced the commutator. There will be FABC. A mu B, A mu C. Now, how did you know that this part I won't do now very carefully today? Just, I don't remember the sign. I think the sign is correct, but I don't want to worry about that. We just want to ask you physically, how do you know that there will be an extra piece?
Covariant derivative. Covariant derivative.
No, physically. Yes, I agree with you. Mathematically, it's clear that it will be there, just from the way I written that I agree. But physically, remember what I said, they carry charges. They interact with themselves. They should be reflected in the theory. You cannot carry charge and not to interact to say a photon. Or you carry this charge, you will interact with a guy that has a charge, that is a messenger.
With each other.
Precise, because they know each other. They carry charges. They are not trivial. There are non-commutations here, okay, which are very important. So I knew, if I think a little bit, this is the sort of structure invariant of the group, okay, covariant. So even with some physical, intuitive, if you wish, approach, you will figure out that, of course, that doesn't fix the coefficients. It's all interaction. Let's forget it at the moment. I'm going to mention this here just to show you something. And it's very important that you shouldn't be fooled, because people keep being fooled. People my age, people any age, and I say any new generation, being fooled in the following. That some 40 years later, a theory which made many predictions whatsoever with the real world is still the most promising theory to look at. I still get some of you guys telling me I have to work on string because this is going to be the theory of nature 45 years later. Not a single prediction emerging. You should worry. Go back to the history of physics and you will see whenever there was a theory that would make sense, it would be sort of happening. One revolution, one understanding, one discovery after another. Look at this era in the next 15 years here. This is 1954. I mean, you may work on whatever you like to work. I'm sorry if I preach from time to time. Do it because you love to do that. But if you want a physical motivation, I suggest you work on the theory that made some contact with the real world, that make predictions that people tested. Okay, that should be a better bet. Okay, so now this is what we did on Friday. We pretended that we knew this, and I'm sure you did know. And then we said, well, it's trivial now. The first step is going to be easy. If I want to build a unified theory, by that time, of course, what I knew, 56, we learned that parity broken. And the speed is amazing, okay, but this was sort of an unusual error. There was something incredible. This was only just a few years later after QED was established as the quantum theory of electromagnetic interactions. And from here already in 57 to 58, Marshak and Sudarshan analyzed all the experiments. Feynman and Gallman parallelly suggest the V minus A theory. '57 to '58. V minus A, in other words, it was established that the maxima violation of parity went hand in hand with the vector minus pseudo-vector current. It could have been scalar, pseudo-scalar, whatever, but it had the form, and this was very nice. Once you know that it has this form of vector currents, then of course it can fit nicely with the gauge principle. In the gauge principle, what you have are introductions which are erased. which gets gamma mu there, right? The generalization of the Dirac equation. So in other words, what was known is the form of the effective by 1957-58. Also 1957, Salam and Landau independently suggest the two-component wide form for the neutrino, okay? Which, okay, he often sort of regretted. He would say, stopping short and just thinking of neutrino and leptons and not of other particles, okay? I already jumped at this time. It is established that all of the particles in the weak interactions are simply one parallel. The maximal breaking operity, which I call left. So the theory is GF over square root of 2, and this is, let's say, proton comes out. I write once only a proton, then I turn to quarks. This will be the Fermi interaction. Which is roughly 1 over 300 GeV squared. So if I want to build, okay, recapitulate very quickly and then move on. If I recapitulate, I want to do the Electroweak theory. Well, that means, physically what it means, forget just the mathematics, okay, that means that there is a messenger for the weak force, which I call the W boson. It has to carry charge because it takes proton to a neutron, electron to a neutrino, right? And the form of the weak interaction would have to be, the way I normalize it, G over square root 2, W mu plus, let's say, and then nu L gamma mu EL plus NL bar, no, PL bar gamma mu NL. And what he says is P is UUD and N is UDD. We will, instead of proton and neutron, talk. This is not true in 1957-58. They have no idea of quark that will come some years later. But you and I know a little more and we'll use it. We can also go back just to make sure that we understand it. It doesn't matter what we do. So what happens in the neutron decays? D, so this would be a neutron decay. D goes into U plus E plus nu E bar. Right, this would be a modern version of neutron decay. If I want to build the Electroweak series, it has to be minimally SU2, we said. I need 3 gauge bosons. I need 3 generators, that's SU2. And we tried to do that. And what we found out, first, immediate success. We got W. Interaction produced immediately. W mu plus minus is A1 minus I plus A2 mu over square root of 2. I mean, in this case, the mu is d mu minus I. Pauli matrix is sigma over 2 A mu A. These are the 3 A mu's, and W is built obviously out of the first 2, which are off diagonal. W is off diagonal. W takes 1 charge into another. Which means, by the way, an amusing thing, if you wish, I could write it a little better. If I write my N in U, notice that there is a symmetry between proton and neutron and up and down, right? If you invert P, how much do I have to? 180 degrees becomes D. invert n, it looks like u. Minor point. It's not a big deal if I use Pn or... I'll have to comment on that. This is, however, you could have asked me. Okay, you remember this with on Friday, and this is obvious from here that this is how it's going to happen. Okay, sigma 1 and sigma 2 have this off diagonal 4. The convention of sigma 2 is I get a minus sign here, just convention of sigma 2. The thing, however, I predict in this theory, this is very important, is that Q is T3, or Q electromagnetic. I have no other neutron generator. The charge, when I say that I have a unified theory, or some semi-unified theory, or whatever I say, that there is a gauge group in which lies my photon, that means photon is a linear combination of the gauge fields inside, or the electromagnetic charge is a linear combination of the charges, or generators. There is just one neutron generator in SU2, which is T3 by convention, therefore Q is T3. You can multiply by something if you're worried that normalization may not come right. Doesn't matter whether you put an overall constant. The point here is that this is a traceless generator. The commutational relations guarantee us the property of SUN that this is traceless. Charges are quantized. So from here, by using a doublet, I would predict that the charges are proportional to plus and minus a half. Remember I said the other day this would never work because I have to get 2/3 for the up quark, minus 1/3 for the down quark, and 0 for a neutrino and -1 for an electron looks completely different. But you could have told me, go back to 1957. This attempt was made by Schwinger. You could have said, go back to 1957. At the time, there were no quarks. There were proton and neutron. Notice that the charges of proton and a neutron. So I have neutrino, charge 0, electron, charge -1. Then I have the proton. Let me work with neutron, which has a charge, or anti-neutron, charge 0, and anti-proton has charge -1. Now the charges look exactly analogous. Why don't I work with antiparticles just to see what's happening? Okay. Nothing would happen. This would never, I will never get a traceless situation. These guys cannot live in a doublet. They cannot live in a doublet. Particle is a doublet. Charges must sum to 0.
Why did we also take proton and neutron left-handed?
Well, I didn't want to talk here about whether they're left-handed or right-handed yet, because I would fail. If I take them left-handed, I will get everything left-handed, but electromagnetic directions are not left-handed. I mean, you can say, why do I bug you with this wrong example? Okay, it couldn't have worked. If I don't take it left-handed, then I will not get weak interactions left-handed. So I said there was even a deeper. I love this example because of this failure, of this beautiful failure. This is a fantastic theory. It predicts quantization of charge. This is what you and I want to have because there is a miracle of nature. It's crazy that you and I will have proportional masses to integers to each other, okay? That we want to understand. You spend all the time bugging. Imagine that in your class everybody has the mass precisely an integer of the other. You and I will be discussing this day and night. You know, we got to figure out this miracle. Everything else in nature is continuous. When you have parameters, masses are continuous, but charges are not. And this is a kind of theory. It's a lesson also for future. This is a good theory to start with. Too good for its own good, I may say. Over-predict. But then there will be another problem, I agree with you. I wouldn't know how to build parity violation and parity conservation. Okay.
But maybe we could just put the left-handed terms for leptons, but full functions for full.
No, because quarks are also left-handed. Everybody is left-handed in a weak interaction. Today it was established that only left-handed particles. Okay, now we can look at the polarizations of hadrons in such processes. Okay, and what you have is the beauty of a universality of a weak interaction. So we well,
Let's read it out. We cannot figure it out. Why we don't talk about left-handed or right-handed W bosons?
well,
Because
I don't know if I should answer you. You should. Someone wants to help? Someone wants to comment? Why don't we talk about left and right-handed photon? We don't talk about two polarizations of photon, right? I could even try to introduce that notation, but it's not the thing. The point is the fermions have, I'm not going to talk about scalars, they don't have this characteristic. Fermions like you and me come being left-handed or right-handed precisely. The helicity of the photon, in some sense you could define this, how to say, well, you talk, okay, I don't know how to answer that very well. You do talk of different polarizations of the photon, the transverse polarizations. You could use the language of left and right. It wouldn't do you any good because the photon has completely left-right symmetric interactions. And for W, you see, the question is maybe better than I thought of it. The question is maybe good. I for one should think about that. Well, the W, but let's talk about it in 5 minutes, 10 minutes. Let's move on and come back to my full question. In the end, I will do that. I will talk to that in the end, towards the end of the course. If you turn down in order, I can bet your mouse, I can answer the question. I could do that, but I will need two different W's. Just the same way that I have actually two different electrons. I literally have two different electrons. Okay, we recently talked together because one is positron, one is an electron. We put them together because of the mass term. But strictly speaking, what propagates, what is the underlying quantity, what is the underlying irreducible representation Lorentz group, is a left-handed spinor. And the right-handed spinor has nothing to do with it. It would propagate independently. Electron would have these two pieces. And you could write the theory with separately left and right. It's not so convenient because they mix together and they like both to interact with the photon. So if I were to do this about a W, I would have to introduce another W. But that will be clear maybe in a short while. So you can see the problem is not, it's there independently whether you work with. The quantization of charge will not come up here, right? So let's work with quarks from now on. So we said the minimal, the really minimal extension of the minimal damage, minimal change with a profound, however, change in reasoning would be Glashow comes in 1961. Remember what we are following. We are following the principle that interactions will have messengers. The idea is older than I thought. I learned only in recent years, I'm embarrassed, that Newton in his great work, if you read the Principia, he says something amazing. He says only a fool would, we credit Newton with the instantaneous force at a distance, right? We say, well, Newton was not that, didn't comprehend it at that time, But even different times, then you say, but Newton was not completely stupid, okay? Let's keep that in mind. Newton says only a fool would imagine that there are instantaneous forces. Cannot be that. There must be messengers between particles getting engaged in interaction. But since I cannot coherently talk about that, this is a real physicist, okay? With a discipline to talk about things that can be both probed and also discussed mathematically at the stage where you are, physically, okay? He says, I will simplify the picture. So more than 400 years ago, right? 500 years ago, Newton was already thinking that forces should have messengers. This is what we are doing basically, physically. The Cage principle is simply a deep belief. There ought to be a messenger for an interaction. Therefore, I'm going to stick to the idea that there is a W boson, says Glashow. Well, also it helps you to know that the energies are slowly increasing in your accelerator. So now if you start talking about the W boson, it starts to make sense from the point of view experiment. You can start hoping that someone can reach those energies. So this is 61. He says, well, SU2 failed, so I will write SU2 plus 1. Which means there are 3 generators TA here, and there is a Y generator here, and TI and wave, they commute. So this has a coupling constant G, a coupling constant G prime, U1 has a generator Y, and this has generators TA, the usual. What I mean by the SU2 cross U1 is that they're complete. For example, if I have a doublet, particle in the doublet must have the same hypercharge. For example, can that U1 be charged? It will turn out, I will find out whether it can be, but you can think physically. Can this Y be charged? And if yes, why? Why not? No, because particles in a doublet cannot have the same charge. You have a neutrino and an electron in a doublet. Doublet, it means that you have particles that go into each other under weak interactions. Okay. So this is why I introduced some arbitrary new hypercharge, we call it. And I say immediately that the electromagnetic charge now will be a mixture. I don't write arbitrary constants, they are not useful because this is arbitrary completely. So whatever charge you give me, I can reproduce this by properly choosing Y. The arbitrary normalization is hidden here. This is a U1 factor because of the lack of commutativity or non-commutativity. That's arbitrary complete. I've lost the beautiful charge quantization prediction or glacial loss. And they got it here, the courage and the wisdom to proceed. What it means, in order to produce the weak interactions, and we often write this, SU2 must be left-handed, we say, or maybe, sorry, it would be better to put it here. That means, okay, so this is my gauge group. In other words, I can write immediately covariant derivative. Let's do it here. Once I tell you the gauge group, notice that the messengers are fixed. I will have minus GA, TA, MUA, you agree? This is my SU2 coupling constant. Minus I, G prime, for SU2. And I'm going to call this Y over 2. It was done historically, so I stick to it. Like here. There are two charges, so we cannot, we don't have the same strength, we don't really unify. There is a mixing angle, which we call weak mixing angle, which is defined, just a definition, right? I have a free parameter. In a truly unified theory, G prime would be equal to G, and I would predict that this is 45 degrees or whatever. It's not that fundamental, as beautiful as it turned out, okay? We have a free parameter. I will have to describe all the interaction in terms of the weak mixing angle, okay? So what do you mean? So when you build a theory, you specify your gauge group. Once you specify your gauge group, that's equivalent to specifying messengers. Then you have to specify the matter. Matter is what you and I are made of. This is fermions. So the next step, you specify your underlying particles, fermionic particles, which are quarks or leptons. And now you know what I mean that SU2 left means that up and down quarks, doublet must be left-handed. Only left-handed guy will couple to W. Nu and E doublet must be left-handed. What about right-handed? I know that the right-handed fermions exist. What about them? I want to show you that once I tell you the gauge group, we ought to be able to figure out everything by knowing the physics. Remember, W goes together with the generators, which are Pauli matrices. Okay, so W can only couple to the particles in a doublet. When I say that this is a doublet, this is equivalent to saying that TA here is sigma A over 2. Right? Any group, we can imagine different representation. That means taking different TA. We start with the fundamental one, but we build other. So what about right-handed fermions? Can they have weak interactions?
Yes. But they have singlet advantage.
No, they cannot have weak interactions. You said yes. Only left-handed fermions can have weak interactions. Okay, that's what I've been told by Madame Wu, Lederman, and all those guys.
Or maybe we just have left-handed particles everywhere and we don't see the right ones.
Oh yes, we do.
You see the ones?
Yes, we do. If you go to sufficient low energy, you can change the left-handed particle into a right-handed particle through the master. There is a helicity or chirality change with the mass. Remember, only if the particle is massless. Then you get helicities. Then helicity UL, remember, was minus a half UL. And helicity UR was plus a half. Why did I write QFL? Because normally I write a two-component spinner, which is to say this is a fermion. I can change the color. There are right-handed particles. It's very important. Not only that, who interacts with both left and right? Photon does. Interacts with the right-handed electron. Remember what you had in the homework. You've learned that the charge conjugation takes left into right. So if you talk over left-handed electron and the right-handed electron, you can also talk over left-handed electron and the left-handed positron. It's the same thing. Because when you go from particle to antiparticle, chirality changes. And this is another way of understanding that charged particles must have both chiralities. They're also massive particles, okay? There are no charged massless particles, and you will see that that fits together. So photon couples to the positron, or the right-handed electron. So there is a right-handed electron here, ER. And there is a right-handed quark. And there is a right-handed quark. And there could be a right-handed neutrino, but we are going to build a minimal standard model as Glashow, Weinberg, and Salam did. And nobody ever saw right-handed neutrino, so we are going to say minimal means I just include the particles that exist and include the interactions that exist and try to describe it. Okay. That's the principle of mimality. That's what Einstein does when he develops the theory of gravity. It's the minimal theory. How do you know that they are singlets? Well, you said correctly. Part of your statement was not correct, but the other part was correct. Yeah, they are singlets, okay? That means, of course, that the generators act as zeros on them. They do not transform under the V group. They will never see the double boson. Or the double boson will never see them. But they are there. Now, I have this fundamental formula. And from here, I can find the hypercharge for every particle. 2y is q minus t3. Let me see if you can tell me reasonably quickly, what is the hypercharge of ER? What do you think is the hypercharge of ER? How do you read this formula?
Q plus 1.
Q is minus 1.
1 over 4.
Did I write correctly? Why don't I put 2 here? Would be better, maybe.
Minus 5. No, it's okay.
Maybe this will be better from there.
Minus 2.
It's 1.
The other was good, but this is better. Okay? No.
It's 1.
Q is minus 1.
Minus 2.
Minus 2, please. What about UR? twice the charge, 4/3. What about ER? Now this you tell me. Minus 2/3, thanks, twice the charge. What about UL? Now it's a little tricky, you have to keep both.
What's UL? Oh, yeah.
Uphand, left-handed upward and left-handed downward. Now you can go and compute it from here. You substitute Q is 2/3, T3 is 1/2, and then you, well. But you can also notice that well, can you do that while I am patiently waiting, or can you tell me what is the hypercharge of the upper? Well, I write down UL is equal 2/3 minus 1/2 is 1/6. 4/6 minus 3/6 is 1/6. So this is 1/3. YDL. Do I have to do this calculation, YDL? No, it must be the same. Remember, these two groups commute. The hypercharge of every multiplet, if I take a 5500 multiplet over to whatever, they all better have the same, whatever is the some big charge. So it has to be 1/3 and minus 1/3 plus 1/2 and so on. You will see it's 1/3. So if you know that, here is a trick to do it more quickly. The sum of the hypercharges will be equal to sum of the charges because T3 cancels in a multiplet. So in other words, if you have y1 plus y2 in a doublet, which is 2y of a doublet, is equal to q1 plus q2 from that formula. This is the formula to remember in a doublet. Am I right? No, there is a 1/2. There is a 2. y1 minus y2, 2y is 2. Sorry, there's a factor of 2. Okay? So y of a doublet, in a doublet here, in any doublet, y is q1 plus q2. So if they find some new quarks tomorrow, okay, they won't, it seems. Seems that what we've seen is there. LHC is not finding new fermions, okay. It could easily reach higher energies, and we'll talk about how heavy can the standard model fermions be. But if they were, you and I could easily figure out in a doublet immediately. Hypercharge is the sum of charges. So here is 2/3 minus 1/3 is 1/3. Here, for example, will be minus 1. But these are just numbers that are not so important. Remember the charges. You can always rederive that. Don't learn too much by heart, okay? What I need you to know is always, if I give you a group, you have to be able to tell me what the T3 is. Or whatever the associated charge. And the charges we'll have to remember.
How we associate the T3 quantum number to which one is 1/2 and which one is minus 1/2?
Yeah.
The doublet. How we determine this?
Yeah, well, how do we determine? I should ask you. I'm sorry. I feel I ask you. I said it here somewhere.
It's T3, so it's
Sigma 3.
sigma 3. But I mean, which one is the minus 1? Which one is the plus?
Right. It has to do with sigma 3. That we fixed. There's a convention in that, but the convention we will never touch. You can do anything you want, but you're not allowed in this course to change Pauli matrices, okay? It's a no-no. I won't let you do that, okay? I want to give you complete freedom, whether you want to listen to me, whether you want to use your own metric, whatever. We got to use the same Pauli matrix.
But you could have written, instead of UD, DU, using the same Pauli matrices. So
Yes, this is my question.
I could have written,
I mean, reverse the.
I'm
Reverse,
sorry to say my answer was not so smart. Good. Okay.
To reverse
Good,
the.
good, okay.
the-
All right, I take it back. I'm sorry. Good. So how do you know? Well, here there is another convention. Notice I have another convention. The particle with the bigger charge is always an upper component. Because of the convention, okay, the charge is fixed. So this has to be an up quark. And it has to be a neutrino. Neutrino has more charge than the electron. Remember, a -1 is smaller than 0, okay? Not the absolute value. The charge as look, for example, there is another doublet, just to appreciate that. This was a very good question, okay? I thought better than I took it, okay? I take it back. I could also write another, look, this would also be a doublet. But I have to put the positron above the neutrino. Why? Because positron has more charge. It has charge +1. And if I want to have another doublet here, I could use d bar and u bar. And by the way, there are people who, are quick to using this, and you should be able to do that. Left goes to right under charge conjugation. So either the doublet is neutrino or the electron left-handed, or the positron anti-neutrino right-handed. This is completely equivalent. If you remember from your homework, charge conjugation, going from particle to anti-particle change, chirality, okay. I could work with this. So it was a good question. Thanks. The guy with the heavy, with the more charges, an upper component. So if you decide to work, by the way, if you and I decide to do grand unification one day, whether we should or not, I don't know. But if you decide to do that, then you should be able to work with the fields of the same chirality. You want to put them together in some bigger representation. So for example, if your quarks are right-handed, your leptons better be right-handed. You can't, otherwise you'll break Lorentz symmetry. Notice I cannot put here a right-handed particle, here a left-handed particle. That cannot happen. I'm assuming that Lorentz symmetry is a good symmetry. So I didn't say it, but obviously I meant it. The symmetry here is SU2 cross U1 cross Lorentz. Okay, they commute, all of them. So in a multiplet, I can put only particles of the same chirality. Very good. Okay. Yes.
This is the same because we take particles as masses in the theory.
The what?
When we say we cannot put right and left-handed chiralities because of the Lorentz symmetries, we mean that Lorentz symmetries should preserve the left and right chirality because of this.
Yeah, of course.
And
If you have a left-handed particle, it stays left-handed.
when it's masses, right?
The left-handed particle stays left-handed. I need to put the mass term in order to change it. But this is the original. There are no masses here. I didn't write the mass term. These are the original fields that propagate. This is the notation I would use to write the kinetic energy. Remember, it is the kinetic energy that defines the gauge interaction. My thing is then we have to worry about whether left can turn into right, and it can. But at this point, I'm separating them. I'm looking at the irreducible representation of the Lorentz group. Oh, talking about mass is going to drive me crazy and you even more, okay? We are going to have to relearn everything in order to talk about masses. I cannot even write the mass term for these guys. Now that you ask me. This is the problem that Gleshow faced. And I talk about what he said, okay? He was not completely stupid, Gleshow. But he faced the problem, how can he now write the mass term? Because one fermion is left-handed, the other is right-handed mass term. But one is a doublet, the other is a singlet. You cannot write an invariant out of a doublet and a singlet. One is spin half, the other is spin 0. There is no invariant out of two of them. I can write invariant out of two spin half particles, of course. Or two spin 0 particles, but not the other way around. There is no mass term here. Okay, this is going to be the cause. The standard model means understanding that and talking about the Higgs boson and all that stuff. Okay.
But it is safe to assume that for all other interactions that the particles are practically massless for weak interaction or for EM or anything.
Well, particles, look, it's like this. If I go to very high energies, I can forget their masses. They tend to be irrelevant because at high energies, the mass term is the higher the energy is less and less important. So eventually it becomes harder and harder. to change the, at LHC from as a massless, of course, okay, electron. Massless, right? Imagine the mass of 0.5 MeV with the energy of hundreds and hundreds of thousands of GeV. But I want to be able also to describe processes at low energies, therefore I have to be prepared for that. I will have to have I need a complete theory. So this tells me how the particles should propagate under their respect, what the kinetic energies will be, and they can go into each other, okay? When they go internally into each other, I want the group to commute. To commute with Lorentz, it means that they have both the same Lorentz properties. That's why they have the same hypercharge. For example, these two guys must have the same color. They actually, this is not, I'm simplifying our life. There are actually 3 up quarks and 3 down quarks, but they have better have the same color. Because W boson carries no color. W boson is blind. Cannot see color. So I don't have to write color. Okay? It's color blind, we can say. And let me show you why we want to proceed. You might say, well, what's a big deal? I'm not so excited. This is 1961. We are very far from the energies of finding the W boson. It's going to take another 20 years or something. Now, looking back now, 20 years, I can imagine how he must have felt to a young man like Lesho, 20 years. He was a postdoc at the time, I think, in Copenhagen. Looking from my perspective, we've been waiting for LHC. 20 years looks like a short time. We are waiting for some new physics beyond the standard model for 30-some years. Okay. Well, we know that neutrinos are massive, so it helps. But nothing at the accelerators. So, the first fundamental prediction, this is why we want to take the theory seriously. Because you can object, well, what's a big deal? Okay, how can you fail here? It's trivial. We added you once, so whatever charge I give you, you're going to tell me the hypercharge. Well, I don't know. And then, of course, you have a messenger. Well, who's going to observe that messenger? Okay, we got excited. I was a beginning graduate student in the early 70s when this was becoming a theory. Okay, I'll tell you the history. It's sort of amusing. You may have heard it from Alexei or other people. The amusing part is when Glescher wrote the paper, nobody paid attention. Here is the ground-breaking touch of a genius and nobody pays attention. Even Glescher doesn't pay so much attention. It's hard to take yourself seriously when nobody else does. In 1964, Glescher writes a beautiful paper with Bjorken. You heard of that, suggesting a charm quark? I'm sure Alexei mentioned it. Okay. It's good to repeat it. He even showed you how charm quark has to be there because of the K long, K short, and so on. We repeated that. And look at that Glescher paper. He doesn't cite Glescher. 1964, he doesn't cite his great work. I find it mind-boggling. And this is the thing. Now I have to reproduce the electromagnetic interaction. This is important. So I have A3 and B, you agree? I have 2 neutral gauge bosons. How do I know they are neutral? Where B corresponds to the hypercharge, which is U1, which is obviously neutral, diagonal. This is diagonal, it commutes with everything. And D3 is also diagonal by convention. Okay, this is Cartano SU2. So A3 must be some linear combination, you agree, of photon and some other field. A3 cannot be the photon because photon doesn't couple to T3. Photon cannot be B because photon doesn't couple to hypercharge. Hypercharge must be the same, but up and down quark do not have the same charge. So I'll just say that this is some linear combination of A and B. If I don't write the Lorentz index, doesn't matter. Let's not write. Let's take it at the end to have as simple notation as possible. Then B must be orthogonal. It's orthogonal to A3. That means this is cosine theta A minus sine theta B. They are orthogonal field. I've started with them being orthogonal, they must remain orthogonal. So if one is one linear combination, the other must be orthogonal linear combination.
There A and B is photon and another field in the right hand side.
Maybe it's it was good, but maybe it would be better if I introduce another. I think it was Glashow. Did Glashow or Weinberg call it Z? I don't remember now. I think it's Weinberg. Saying, oh, I thought this is going to be the last Cage boson ever to be seen, so they put Z, which is very funny. Now we call new imaginary gauge bosons of grand unification X and Y. You know, they come. Anyway. I may have to sit down a little bit from time to time. I went skiing and I had a bad fall and my knee is hurting. I had an old knee injury. Any of you guys ski? Do we have anybody who tries skiing? Well, I guess you're too busy. It's not. It takes a different position. It's not. I didn't ski when I was a PhD student. I wanted to. It took me a long time after all. It's a pity that you should be able to organize something, take it to the snow. It's the most beautiful thing in the world. Anyway, by the way, I discovered it late in my life here, when I came to work here. So, and the original interaction will be, remember from covariant derivative, which is there. You agree there's going to be G, T3, A3, plus G prime. There will be, of course, some psi bar, gamma mu, and there will be some mu index. I'm going to focus just on this one. And y over 2 I'm going to call q minus T3, B. Agree? So I'm going to write the B index and so on. So what do I have? I have G. No, I have T3. Let's take T3 separately. T3. I have GA3. G. A3 is sine A. I will write this is S and this is C for simplicity. So I have SA T3. No, I don't have right. It's a pity to make a mistake. So we are just carrying this. This is G, T3. A3 is SA plus CZ plus G prime, Q minus T3. And this is CA minus SC. T3. Let's look at A. A will go with GS minus G prime C plus Z GC plus G prime S. This is the T3 piece. Please check me. I think I'm going okay now. I know what I have to get, but I may be making mistakes, you know, which cancel themselves. So. Plus, this was T3, let's write Q. Plus Q, what do we have with Q? We have G prime CA minus G prime SC. I think this is correct. I'll pause. Correct? I think it's correct. Tell me when I can go on. Can you guess? slowly what is happening. Now, I don't know how, I'm Glashow, 1961. I know that the photon is massless. I know that whoever comes new is whatever this guy did. It's not massless because we would have seen it. So he knew this guy was going to be heavy. So, but he doesn't know how, you see, there is some breaking of symmetry. Notice, I started out with SU2 cross U1. Everybody is massless. At the end, the symmetry will be broken. He doesn't know how to break it, but he says the following. I know I must reproduce the photon. If my theory is to make sense, the photon must have the usual electromagnetic interaction. So I'm not going to derive them because I don't know how I get the photon. I don't even know, I cannot prove that one guy remains massless. You agree? He doesn't know anything. He doesn't know how gauge bosons are getting or not getting the mass. But he can say the following. Let me assume that there is a photon, and then let's see what I get. And we know everything. I know, and you will see now, everything then will follow. So what does it mean if I say that there is a photon? Well, the photon must couple. Remember, this is the photon. Psi bar gamma mu q psi a mu e. This is the photon. This is the definition of the photon. It couples to a universal thing called electromagnetic charge and has a universal coupling that we call E. What does it mean? That this must be 0. It doesn't couple to T3. Which tells you that, notice what here tangent theta is. It's precisely this weak mixing angle. So I've just proven from here that theta is theta double. In other words, this is the way. Let me use the privilege of the blackboard. The strange mixing angle between the gauge boson is precisely the weak mixing angle. This is reassuring. I don't have to introduce another parameter. Now, up to now, I have only one parameter, okay? I feel already better by this fact. And also, it tells me, it gives me immediate prediction. It tells me that E from here is G prime cosine theta W, which is immediately G sine theta W, the way I define theta W. Here is a fundamental prediction of Glashow theory at this point. It's not yet a complete standard model. It says that weak interactions are not weak at all because E is actually smaller than G. Weak interactions are strictly speaking stronger than electromagnetic. The reason that they looked before very weak, you were at very low energies where W would become so inertial it couldn't move. If your messaging cannot move, the weak interaction becomes weak. The interaction becomes weak. This is why we know there may be many new interactions that we are, not we, I mean they are looking at them, we are hoping that discovering, we all are betting that it had to be some new messenger, some new gauge bosons, okay? We have to imagine that this is the whole story. But we know they will be very heavy because we have not seen these interactions. LHC could see them. So this is crucial. These algebraic things, we will be deriving the things, I'll be reminding you of hypercharges and so on. Oh, we raised the representations, okay. On Wednesday we'll okay, here is the definition of theta W. Tangent theta W G prime over G. Of course, he didn't know at that time. Remember when we exchanged the W boson the other day in order to reproduce the weak interaction? D quark becoming up quark, emitting a negative W that becomes an electron from neutrino that enters. This is a weak interaction. Or the weak interaction, this is the beta decay, neutron decay. we said that G Fermi over square root of 2, we found out, was G squared over 8mw squared. Remember that? From the way normalized, I made a mistake. Where did I write the weak interaction? There is a factor 4 in that formula. I always forget that because I put it is this G over 4 square root of 2. Psi L, let me not write it left-handed. If I turn out of left-handed, then there is a 1 over 4, because people just write 1 plus gamma 5 or minus gamma 5, and then the form disappears, okay? But left and right have a half. So we derived this, you remember, by exchanging W, okay? Because we said the propagator of the W was G mu nu minus Q mu Q nu over mw squared Q squared minus mw squared. And in neutron decay, Q is basically 0. Proton-neutron mass difference is basically 0. It just decays. This is why the lifetime is so long. Instead of 10 to the minus 6 seconds or even less, it takes neutron 10 minutes to decay. Okay, so I can safely ignore Q, and I get 1 over mw squared. And then we put the factors. Each vector has G over square root of 2, and I get this formula. Notice that I can write as E squared over 8 mw squared sine squared theta w. And from here I have a prediction immediately. mw sine theta w is about 40 GeV. You can put the numbers. You didn't know theta w, so you couldn't really predict mw, but you could say, look, if it's some reasonable number, I get it.
Does theta w is like universal constant, doesn't change at all with energy or
What?
W, theta w?
Theta w. Well, theta w is a ratio of coupling constants. And as I said, you know, this is sort of the most beautiful thing in field theory, if you wish, is that the constants are not constant. They do change with energy. Everything changes with energy.
But the ratio doesn't. The ratio changes, so.
I don't know, why should the ratio remain the same? That would be very strange, because G prime and G should probably evolve differently. They correspond to different gauge interactions. So my guess would be, well, it's an educated guess, I know, I'm sorry, I'm cheating. It changes a lot. For example, if you come to the energy if you come with the energy, look at this energy, okay, but no laugh. If I like to some X energy, we call it 10 to the 16 GeV. Now you may say, why would a reasonable adult talk about the energy which is 14 orders of magnitude bigger than the, you know, W mass? I just understood W mass. It's like you're saying, oh, I understood the motion of a car, so I'm going to take the same Newton physics to 14 orders of magnitude smaller. You would fail badly. Okay, this is what happens when you're too ambitious. There are all kinds of things that will happen to you. Anyway, here, for example, sine squared theta w becomes 3 over 8. And today, sine squared theta w, you know what sine squared theta w at this energy, Ex. Do you know what sine squared w is? It's often cited as sine squared theta w today. So we say at the scale mw, that's what we'll define today as the scale of the new interactions, okay? The scale of weak interaction is the mass of the messenger. So it's nice to define it here. Do you know what it is, roughly? It's about a quarter, right? Someone said a quarter. It's 0.23. I will often say it's a quarter. When you do the calculations, when I give you some homework, put a quarter in, because there may be things that cancel, okay? Well, if you have, of course, today we have calculators, so it may not be. I like to get things analytically. I'm the last of the Mohicans. I don't even like to use a calculator. That, of course, I'm soon going to be extinct. I never use the computer in my research, imagine. And I'm cheating because my papers have a lot of computer studies, but I've never. Obviously, someone else does it. So I would remember it, that theta W is 30 degrees roughly. If you take a half, theta W is 30 degrees. But you see from a quarter it changes to 3 over 8, right? So there is a change. Well, it's not that big. See, we say that the coupling constants run. I told you already, it's a terrible expression. We should call it crawling coupling constant. It's logarithmic, the change. In the first approximation, you can forget about it as people used to. People didn't know that the coupling constants would run. Theory preceded experiment. It didn't matter because you would do experiments from, 1 GeV to 1.5 GeV. That forget the running. We are aware of running because we went from not just from MEV, from the era of accelerators of GeV, right, went to the hundreds of GeV at lab and today thousands. And of course the running, the change becomes appreciable. Why it's so important, this running? The fact that some coupling constant changes a little bit, take electromagnetic or weak, they were already small to start with. But the strong coupling constant, thank God that this happens because otherwise you wouldn't know what to do. The thing is when you go to high energies, if it's true that the coupling constants change and it seems that they become smaller, you will see. Weak and strong coupling becoming smaller. That of course allows us to be able to do, this is why we can study LHC physics. Strong coupling becomes weak by the LHC. And you can do perturbation theory. You've heard of this. Alexei talked about that. He showed me more or less, so this time I had a look, or at least he showed me what is in his notes, okay? It's not a proof yet that he actually talked about that, okay? But we went over that, and the other day, just to see it to be a little more uniform. And he sort of showed you how you could sort of pretend that there are no gluons, quarks are almost free, but then it's a little better if you include it, you can do it systematically and you can do nicely perturbation theory. So since you asked this question, I can tell you the situation at the weak scale. Sorry, let me just write this and then I'll let you go. I forgot to write the Z interaction. So in other words, from the photon, now I can predict the Z interaction. And I will get the Z boson coupled to T3. I'm going to take I'll put the Z. I will take G over cosine theta W out. It's a convention. Okay, just a few more minutes. So T3, look at T3. If I take G over C down, then I'm going to have C squared here and S squared here. That's 1. Okay. So I get coefficient 1 minus Q has G prime, which has tangent. So I get S squared. I took 1 over cosine theta W. I get the famous this is the way the Z boson interacts. Of course, there would be psi bar gamma mu. It would be G over cosine theta W. Psi Z mu. I didn't write the mu index, but I understand. There was no need to write all these things because the neutral interactions do not change particles into other particles. Therefore, all I need to know, like in the case of photon, what does photon couple to? Photon couples to Q. The Z current is universal, just like the photon one. It's a little more complicated. Z boson knows also about whether you live in a doublet or not. Photon doesn't care. I don't care how you distribute your charges, whatever is the complicated theory that you start with. You made like some SO10 theory for some reason, okay? Photon says, I don't give a damn, just give me the charge and I'll couple to it. Okay, this guy wants a little more. He says, you must tell me the distribution of these charges inside SU2. See, this happened because we tried to unify weak and electromagnetics, so we got some more information. But notice what is nice here, that I just need one parameter to predict hundreds of different processes. Now I can take neutral scattering, anything I want. Neutrino on the mu, neutrino on the electron, neutrino on the up quark, electron on the up quark, electron on the down quark. process after process. And you can imagine excitement when in the early 70s, why we had to wait 10 years is the fact that people didn't know how to compute in the theory, and it starts in 1961, the first gigantic pass of glacial. Then there will be Higgs mechanism and all that we'll talk about. In the early 70s, 1971, 72, at HOP shows that the theory actually is just like QED. It's a finite theory, you can compute things. Renormalizable, it's fancy language that we use, okay. And then people started, they went crazy. And it turned out that with that one value of sin squared W describe all the processes. Okay, back.
This term that when Z interacts with the Q, electromagnetic Q, through the Q, means that when we draw QED, when we try to calculate QED,
you
include this.
Eventually you have to include the Z boson, yes.
So like electron scattering?
Eventually, in a certain percentage, I think when you come to alpha to the 4, you will start, okay, so there are people that used to worry. The coupling constant change, we said. I said, well, we didn't say, I said. Someone else said maybe. Well, electromagnetic one grows. And it turns out it wants to explode. It becomes so big. In the end, your perturbation theory breaks down there, okay? But you could, strictly speaking, get an infinity. At some huge energy, it's called Landau pole. I remember when I was a PhD student, it used to drive me crazy because people would talk seriously about that. And I couldn't, for the life of me, figure out why. The energy was 10 to the 130 GeV. Now, why the hell would you care about what happens at 10 to the 130 GeV? At 10 to the 19 GeV, gravity becomes strong. You have no idea whether physics changes completely. When gravity becomes strong, all hell breaks loose. Nothing that you knew how to compute. Just to give you an idea, QCD emerged in the early 70s. We still don't know how to make computations in QCD. The non-perturbative ones. They are done on this Monte Carlo complicated simulations, computer one. Nobody knows how analytically to compute it. 40 some years later, we are still struggling. We probably will never know because strongly coupled theory are disasters for us that are used to perturbation theory. So there was a Landau pole, call it energy Landau, which is 10 to the 130 GeV. At that point, electromagnetic coupling would become too strong. But you see, you're saying, why would you worry? Now you and I know, for example, if I want to do eventually what Mehmet asked me, I have to include the Z boson. So forget it, there is not just QED as I go to higher energies. And then probably something new will happen. And there are a class of series where this is cured. The theories began on non-abelian gauge symmetries, which are called grand unified theories. They cure this problem, okay? So what you have to know is that tendentially, we'll have to talk about it eventually, coupling constants do change with energy. The abelian one, U1 grows, non-abelian one, and this is very gratifying, becomes smaller and smaller with energy. So QCD becomes weaker and weaker. So let me give you the numbers, okay? That I've already written it. That, what have I written? I gave you sin squared W. Well, that tells me, for example, alpha electromagnetic at MW. Someone heard of this number? It's not 1 over 137. It's 1 over 128. Alpha weak at MW is going to be bigger or smaller? Bigger. Sin squared W is small, it's a quarter. So get roughly 1 over 30. And alpha strong at MW is not strong at all. It's 1 over 10. This is where you can do beautiful physics at machines like SPS, LEP, whatever, LHC, even better. The coupling is becoming smaller, so people now do better and better perturbation theory with strong coupling. And this is why we can make clear predictions of what should happen, or fairly clear prediction of what should happen at the LHC. So what I did today, now we have to sort of, this was fast, so it may have been too much, I'm going to go down on Wednesday, but we built the standard model. we have to understand what we build. We don't know yet how to compute, we don't know how the symmetries will be broken, we don't know why Z has a mass and photon doesn't have a mass, all of that. But at least we know structurally. You see, this courage, this thought, this intuition, this feeling a glacier had, okay, did a miraculous thing. Many people say that this theory is ugly. People will tell you that it's ugly because charge is not quantized. Some may tell you, I will never use this word. I hate the fact that parity is broken by foot. I can believe that God is left-handed, as I say, but not an invalid. I can find all kind of faults, but it is, I think when people say that it's ugly, it's a terrible, ugly way of speaking, because the beauty of a physical theory ought to be measured by the amount of predictivity and simplicity and the depth that it offers you. Okay, so people often tell you that it's ugly because of the great ambition to say, oh, for example, why are masses what they are? Why is this value of this coupling constant this what it is? Okay, that's being over ambitious. Okay, I want you to appreciate that we have one parameter that will describe hundreds of different processes. Okay, that should be considered beautiful. And they will make some other beautiful predictions. One will fail. I have to stop here. Neutrino mass, fortunately. And you and I have some food to chew on, to think of what could be the new road. Okay, but it's got to start with neutrino mass because that's the only place where we stop. So the journey has started. At the end of the course, you won't know much more than what you know today. But I hope that you know deeply that you will understand what is going on. So this helps you not to be really scared that there is not that much material, okay? We have to really only understand more deeply this physics. And a bit of color. Any last question? Public question before we turn the machine off. That's it?